In this installment, we are going to speak about equilibrium. So we have equilibrium, which means balance. And there are two types of equilibrium we are concerned about. There is static equilibrium and translational equilibrium. And there is disequilibrium, which we can understand it means not in equilibrium. So static equilibrium occurs when things are stationary. So let's imagine we are looking here in this restaurant and we see this lady over here sitting in a chair, like so, and there is a force of gravity downward, and the chair is providing a normal force equal and opposite in that direction. Equilibrium, the two are balanced, the acceleration is zero. And of course, we could do that with every object and every person in this room, the table on the floor and so forth. Static equilibrium means that the forces are balanced. And if we looked at this from a Newton's second law perspective, well, we have our net force is the sum of the forces, ma, then in this case would be Fn plus Fg. The acceleration is zero. So therefore, the force normal is equal and opposite to the weight. So that's pretty straightforward. We could look at persons on a chair or things on the table. So it becomes very, very clear. They're stationary, the forces are equal. We have balance when they're stationary. Translational equilibrium is when there is movement along a straight line or axis. And when we use the word translational, similar adjectives would be rotational or vibrational. So translational means moving along in a straight line. And we could make some connections here to chemistry and your knowledge of matter. Vibrational energy is what happens to the lattice in solids. They vibrate back and forth. Rotation is what liquids are able to do. They're able to spin and roil. And translational is what gases do. They are a molecule, whether they're monoatomic or diatomic, and they're traveling in a straight line at some velocity. They may also be rotating and vibrating, but the translational aspect is that part of it moving along an axis in a straight line. Well, so here's this picture of the people in the restaurant, but I tricked you because this picture that I took in the restaurant that looks like this, it's about this image here, is actually taken in the dining car of a moving train. You can see the countryside passing by. So it is true that we have this lady sitting on the chair with the force of gravity and the force normal, like so. And in this dimension, the z direction, the forces are balanced. There is equilibrium. But what is happening is this train is moving, is translating in this direction toward us, out of the picture, out of the page. It's moving toward us. So it is an equilibrium in the z dimension. It is also in equilibrium in the x or y direction. The velocity is constant. So this system, the lady and the chair, is being translated down an axis out of the page at constant speed and constant velocity. And so that's what we mean by translational equilibrium. When a system is in balance, but the system itself is moving through space at constant velocity. So the difference between these two situations is merely one of frame of reference. Let us investigate this further. So let's take our lady and the table on the train. Or she's sitting in the chair, like so. And we know the forces are balanced, like so. And then we can see that she is in a train car, that is moving along with some velocity v in this direction. But she and that train car are, of course, on the planet Earth. And the Earth itself has, you could consider it be a translational velocity, because as it goes from here to here, it's pretty much a straight line. The Earth is so large that at a large scale, or it appears flat. So we have a straight line. There's translational velocity that way. But there is also the Earth itself in translational velocity in its orbit around the sun. And for those of you who love astronomy and astrophysics, well, you may know this is a very bad drawing of a spiral galaxy like our Milky Way. And we happen to be about 2/3 of the way out on one of these arms, traveling in a velocity like this. And of course, then the Milky Way is moving through space like this on a translational axis. So there is a lot going on here, and it speaks to volumes about our frame of reference and how we're defining the system. And sometimes it doesn't matter if the system is stationary. It doesn't matter if it's translating, because we're only concerned with what's going on in that particular setting. In this case, the lady sitting on the chair. There may be a different context where it would matter that the entire system of the railway car is translating, and so forth. But the frame of reference here is a big deal. Now, of course, I've already mentioned, the law of inertia. Objects want to keep traveling and maintain their current state of velocity, and that's why systems move and translate along particular lines. It's the law of inertia and also conservation of momentum. Because unless there's an outside force, an object wants to maintain its current velocity, whether it's 0 or some number. And that, my friends, leads us to disequilibrium in Newton's second law. Newton's second law says the net force is the sum of the forces involved. And if the acceleration is 0, then the sum of the forces must be 0. Equilibrium. But if the acceleration is not 0, it is non-zero, why, then these forces over here are not balanced. They are, as we might say, in disequilibrium. And when things are in disequilibrium, they accelerate. And this is why it's so very important to observe the nature of the motion of bodies. Because if we observe constant velocity, that means equilibrium, either static or translational. But if it's accelerating, that means disequilibrium. And so that is our tour into the world of static equilibrium, translational equilibrium, and disequilibrium.